Hello everyone, I'm Reo Eriguchi. Today I'm going to talk about unconditionally secure multi-party computation for symmetric functions with low bottleneck complexity. First, recall the notion of secure multi-party computation, or MPC for short. In this study, we focus on a scenario with n parties, each holding a private input bit, and they want to compute a function h on these private inputs. The security of MPC ensures that even if an adversary corrupts a subset of the parties, she cannot learn information on these private inputs beyond the output. In more detail, we assume that adversaries are semi-honest, that is, they do not deviate from the protocol. Additionally, we also assume the preprocessing model in which before inputs are known, parties can get input-independent correlated randomness from a trusted third party. In this study, we focus on an efficiency measure called bottleneck complexity, introduced by Boyle et al. This efficiency measure captures the load balancing aspect of MPC protocols. For example, in a standard MPC protocol, some party often needs to send different messages to all the other parties. Then she has to bear communication proportional to the number of parties. So in the context of large-scale MPC, this can pose an efficiency bottleneck. So to address this limitation, the concept of bottleneck complexity was introduced. The bottleneck complexity is defined as the maximum per-party communication cost. For example, in a protocol with low bottleneck complexity, each party interacts only with a limited subset of the parties. So then, the per-party communication cost is possibly sublinear in the number of parties. This makes the protocol well suited for large-scale networks. Now we review the previous results on the bottleneck complexity of MPC. First of all, Boyle et al. Showed that it is impossible to construct secure MPC protocols for all general functions keeping sublinear bottleneck complexity. So due to this impossibility results, we shifted to a special class of symmetric functions. In this context, symmetric means that the output of a function is independent of the order of inputs. Initially, Boyle et al. Showed in the same paper that secure MPC for symmetric functions with low bottleneck complexity could be obtained assuming fully homomorphic encryption. Then, Orandi et al. Proposed a secure MPC protocol for symmetric functions based on one-way functions. However, all of these previous protocols are only computationally secure. So therefore, we can address the natural question, can we construct unconditionally secure MPC protocols for symmetric functions keeping sublinear bottleneck complexity? So now we show our results. In this study, we construct three kinds of unconditionally secure protocols for symmetric functions with low bottleneck complexity. Our first protocol achieves a very low bottleneck complexity of log of n. On the other hand, the amount of correlated randomness is linear in the number of parties. So this means that every party has to receive a lot of messages from a trusted party in the offline phase. So then, our second protocol strikes a balance between bottleneck complexity and the amount of correlated randomness. It achieves bottleneck complexity and correlated randomness both of size n squared. Finally, our third protocol further reduces bottleneck complexity and the amount of coordinate randomness. However, this comes at the cost of giving up dishonest majority. We know that our first protocol was independently discovered by Keller, Orandi, Paskin-Chernyavsky, and Ravi in a concurrent work. Next, these protocols are designed to compute worst-case functions among all symmetric functions. So then we also construct more efficient protocols tailored to more specific functionalities such as the AND function and private set intersection. In the rest of this talk, we will explain technical details of our first protocol and our second protocol. As a warm-up, we start with a very simple protocol for computing the sum of inputs over an abelian group G. In the offline phase of the protocol, a trusted party computes an additive sharing of 0 over the group G and distributes shares to the parties. At this stage, we can see that the amount of coordinate randomness is only log of the size of G. In the online phase, parties communicate in a round-table manner, and each party adds a masked input xi plus ri to a message from the previous party. Then the last party can get the sum of inputs plus the sum of ri's. On the other hand, these masks are additive shares of 0, so it's equal to the correct output. So this protocol implies that, for example, the task of opening secrets can be done with low bottleneck complexity. Before getting into the details of our first protocol, we recall a basic observation about symmetric functions. If a function is symmetric, then the output depends only on the number of ones in the inputs. So therefore, there exists a function f which maps the sum of inputs, which counts the number of ones into the output of h. So then, challenge is now reduced to security computing of the corresponding function f on the sum of inputs. So to address this problem, we use the technique of one-time truth tables, which allows secure computation of a function based on its truth table. More technically, first, a trusted party distributes shares of a random number r, and simultaneously he distributes shares of a unit vector with a 1 at position r. Then parties open masked input s minus r and locally permutes the share vector with a shift s minus r. Then this enables parties to get a share of a unit vector with a 1 at position s. Finally, parties locally multiply this share vector by the truth table tf, and they can get a share of f of s. Finally, they jointly reconstruct shares and obtain the correct output. So now we provide a formal description of our first protocol. Recall that the computation of a symmetric function h is reduced to the computation of the corresponding function f on the sum of inputs, denoted as s. So in the offline phase of our protocol, a trusted party samples a random number r within the range of 0 to n, and he distributes shares of r. At the same time, he also computes a unit vector with a 1 at position r and distributes shares to the parties. At this stage, we can see that the size of coordinate randomness is on, because parties need to get n shares. In the online phase, first, parties open a masked sum S minus R using shares of R. We know that this reconstruction can be done with low bottleneck complexity by using the previously mentioned sum protocol. Next, parties locally permute the share vector with a shift S minus R. Then this enables parties to get a share of a unit vector with a 1 at position S. So then parties locally multiply this share vector by the truth table of F. So then they can get a share of F of S. Finally, again, they jointly open this share and get F of S. So because parties interact only when opening a constant number of shares, so the resulting bottleneck complexity is only log of n. So we have shown that our first protocol achieves a very low bottleneck complexity of log of n. However, the amount of correlated randomness is linear in the number of parties, because this is because every party has to receive n shares from a trusted party in the offline phase. So this can pose an efficiency bottleneck if n is large. So next, we will provide our balancing technique to reduce the amount of correlated randomness. Our second protocol achieves the correlated randomness of size n squared. Despite a trade-off of somewhat worse bottleneck complexity, the overall cost, including online and offline phases, is still sublinear. So in our first protocol, we observe that the computation of F is expressed as the product of n-dimensional vectors. So if we naively implement this using correlated randomness, then we will result in a high offline cost. So instead, based on Chinese remainder theorem, we decompose integers between 0 and n into a pair of smaller integers, each ranging from 0 to p or q, where p and q are primes of equal size n squared. So as a result, the computation of F is now reduced to the product of matrix and vectors of dimension n squared. So this balancing technique allows us to reduce the amount of correlated randomness. Now we provide a formal description of our second protocol. Again, recall that the computation of a symmetric function can be expressed as the output of the corresponding function f on the sum of inputs. Furthermore, we can decompose the integer s into a pair of smaller integers using the isomorphism induced by CRT. And now the computation of f is expressed as the product of a matrix and vectors of dimension n squared. First, in the offline phase, trusted party samples are random number r between 0 and n, as in our first protocol. The difference is that he decomposed r into a pair of integers, r1 and r2. And he also computes unit vectors corresponding to these integers. And he distributes shares to shares of r and these unit vectors to the parties. At this stage, we can see that the size of correlated randomness is only n squared. In the online phase, as in our first protocol, parties open a masked sum S minus R using shares of R. Again, this can be done with low bottleneck complexity. Next, parties decompose it into a pair of integers y1 and y2 using the isomorphism phi. Next, parties locally permute each share vector with a shift yb. We note that the resulting share vector is a share of a unit vector with a 1 at position SB. This is because the homomorphism phi ensures that the sum of components of R and Y is equal to the component of R plus Y, which is equal to S. Finally, to compute this product, parties initially multiply this share vector with a matrix MF. This can be done locally because MF is a constant matrix. So therefore, a remaining step is to securely obtain the product of ES1 and MF times ES2. So, however, this cannot be done trivially because the product of shares does not necessarily lead to the product of the underlying secrets. So to do this, we use a traditional technique of Bieber triples. A technical novelty is an observation that the standard multiplication protocol based on Bieber triples has in fact low bottleneck complexity. Specifically, both bottleneck complexity and the amount of correlated randomness of the protocol are constant per multiplication. To see this, we recall the standard multiplication protocol based on Bieber triples. Assume that parties has shares of secret bits x and y, and the goal is to obtain the shares of x times y. So for that, in the offline phase, a trusted party samples random bits a and b and sets c to a times b, and he distributes shares of this triple. In the online phase, parties open masked bits x minus a and y minus b, and then they compute shares of x times y by using this formula. We know that this can be done locally because it involves only local computation. So therefore, both bottleneck complexity and correlated randomness of this protocol are constant per multiplication. Since we want to compute the product of vectors of dimension n squared, so therefore n squared Bieber triples suffice. So therefore, the bottleneck complexity and correlated randomness of our second protocol is n squared. Finally, we summarize this talk. Bottleneck complexity is an efficiency measure capturing load balancing aspect of MPC protocols. Because it was known that secure MPC protocol with low bottleneck complexity for general functions is impossible. So previous protocols previous protocols are aimed to compute symmetric functions with low bottleneck complexity. However, all these previous protocols are only computationally secure. So in this study, we construct unconditionally secure protocols with low bottleneck complexity for symmetric functions. Additionally, we also construct more efficient protocols tailored to more specific functionalities such as the AND function and the PSI. Regarding future works, it is an interesting problem to consider the optimal bottleneck complexity for computing symmetric functions. For example, it is interesting to consider whether there is a secure protocol such that both bottleneck complexity and correlate randomness are only log of n. So related to this problem, we can also consider, can we derive a lower bound on bottleneck complexity for symmetric functions? Boyle et al. Derived a non-trivial lower bound for general functions, but this is not tight for the specific class of symmetric functions. Finally, in this study, we assume that adversaries are semi-honest. So an interesting problem it would be, can we achieve malicious security unconditionally? Boyle et al. Showed a generic compiler from passive to active security, but it was based on heavy cryptographic primitives. So it is an important problem to remove such cryptographic assumptions. This is at the end of my talk. Thank you.